Frame relay serves as a standardized wide area network, WWAN technology, that operates at the physical and data link layers, utilizing a packet switching method for digital telecommunications channels. Initially conceived as a simplified counterpart to X.25 on the Integrated Services Digital Network, ISDN, Frame relay boasts fewer errors, improved channel efficiency, and enhanced performance due to the elimination of error correction mechanisms. It commonly fits in a circuit-switched model akin to traditional telephone networks, fostering long-term connections between endpoints. Primarily employed as a bridge to interconnect local area networks, LANs, or devices with dedicated links to back-end systems, Frame relay offers cost-effective solutions compared to traditional leased lines. Despite its historical prominence, the popularity of frame relay has waned in recent times with the emergence of alternatives like Ethernet, MPLS, VPN, and broadband services like cable modems and DSL. The essence of frame relay lies in its ability to facilitate economical data transmission between LANs and WAN endpoints, achieved by encapsulating data into variable-sized units called frames. The technology leverages a permanent virtual circuit, PVC, in most scenarios, allowing for continuous, dedicated connections without the need for full-time leased lines. Operating within a mid-range spectrum between basic rate ISDN and asynchronous transfer mode, ATM, Frame relay builds upon the framework of X.25 packet switching technology, catering to networks with minimal error rates requiring swift packet switching with limited error correction. By creating virtual circuits to link LANs to a WAN, Frame relay establishes a cost-effective yet efficient means of extending WAN services. In terms of its technical architecture, Frame relay structures its frame delivery along the lines defined for LAPD, with each protocol data unit, PDU, comprising essential fields like the flag field for synchronization, address field for identification, DLCI bits for virtual connection delineation, FECN, BECN, and DE bits for congestion reporting, an information field for data transmission, and a frame check sequence, FCS, field for error detection based on cyclic redundancy checks. While frame relay forgoes link-by-link flow control to streamline operations, this simplicity accentuates the significance of congestion control measures for optimizing network performance. Admission control stands as a pivotal element in ensuring resource allocation, with parameters such as committed information rate, CIR, committed burst size, BC, and excess burst size, BE, regulating traffic flow to maintain service quality and uphold network integrity. Frame relay's lineage traces back to X.25, bridging the transition from circuit-switched to packet-switched realms by streamlining data delivery for shared access scenarios. This technology, revered for its high-speed packet switching prowess, offers reliable connectivity between devices through virtual circuits, enhancing network efficiency and data transmission rates. Although embraced more fervently in North America than Europe, frame relay exemplifies a paradigm shift towards rapid data relay over error-tolerant networks, setting the stage for subsequent network advancements like ATM and carrier Ethernet to further refine WAN connectivity solutions. Frame relay operates as a WAN protocol predominantly situated at Layer 2 of the OSI model. It boasts two types of circuits. PVCs establish logical end-to-end connections over a physical network, while SVCs resemble the concept of circuit switching in the PSTN. Initially proposed in 1984 to the CCITT, frame relay encountered a setback in deployment due to interoperability and standardization challenges until 1990 when a consortium led by Cisco, Digital Equipment Corporation, Northern Telecom, and Stratacom developed the Local Management Interface, LMI, to enhance inter-networking capabilities. DLCIs are numbers assigned to paths within the frame relay network, retaining only local significance, which allows different DLCI usage by devices communicating. Utilizing sub-interfaces enables the activation of multiple virtual circuits on the same physical endpoints. The LMI Global Addressing Extension assigns global significance to DLCI values, transforming them into unique DTE addresses in the frame relay WAN, thereby improving functionality and management of frame relay internetworks. Through LMI virtual circuit status messages, communication and synchronization between frame relay DTE and DCE devices are established. These messages serve the purpose of providing regular updates on the status of PVCs, preventing data transmission over non-existent PVCs. The LMI multicasting extension facilitates the assignment of multicast groups, reducing bandwidth usage by enabling selective transmission of routing updates and address resolution messages to specific router groups. Additionally, reports on multicast group statuses are included in update messages. To regulate frame relay connections, providers often set a committed information rate, CIR, along with burstable bandwidth known as the extended information rate, EIR, ensuring consistent support for the C rate and potential PRA rate if ample bandwidth is available. Frames exceeding the CIR are marked as discard eligible, DE, and are at risk of being dropped during network congestion, while frames surpassing the EIR are immediately discarded. The Frame Relay Forum advocated for standards that would optimize the use of existing physical resources, allowing telecommunications companies to over-provision data services since clients typically utilize services for only 45% of the time. Despite its initial efficiency, Frame Relay garnered a negative reputation in some markets due to bandwidth overbooking issues, especially in regions influenced by governmental and telecommunication policies. Companies like Stratacom and Cascade Communications were among the early developers of frame relay products, later acquired by industry giants like Cisco Systems, Ascend Communications, and Lucent Technologies. AT&T emerged as the largest frame relay service provider in the United States as of June 2007, with networks spanning 22 states, in addition to national and international coverage. Fragmentation is addressed in multiplexing packet data from various virtual circuits through IP fragmentation, where long packets are segmented into shorter ones to ensure service guarantees. The FRF 12 specification outlined by the Frame Relay Forum details the fragmentation method for voice traffic, illustrating how frame relay frames are broken down into smaller, more manageable segments.